This is lecture 9, and so today we're going to be moving out from beyond the confines of the Earth and talking a bit about how the fact that we are this planet that's living in a solar system it's experiencing the environment of the solar system has then affected life on Earth. And so, you know, the last few lectures we've been focusing on this sort of microscopic stuff of how life on Earth sort of arose and what it is to be alive on the Earth and the biology of that life. But now we're going to take a step back and start moving outward away from our planet, looking at the environment. And specifically this lecture is sort of fun because we're talking about these big extinction events that have happened, we think, over the course of the Earth. Some of them we have pretty good evidence were triggered by big rocks that basically came and slammed into the Earth and created mass extinction events. So we've got a few kind of interesting pictures here, and we'll come back to some of these ideas later on. One of the big things we'll talk about is an event that we have pretty good evidence for that happened about 65 million years ago. We believe a big asteroid that was gigantic slammed into the Yucatan region off the Gulf of Mexico, and this was the event that we think triggered the extinction of the dinosaurs, or at least contributed fundamentally to the extinction of the dinosaurs. The extinction of the dinosaurs is a really big event for us because we think that after that event happened, it opened up a lot of niches for mammals to then take over. And it was really the rise of the mammals and then eventually us that came about after this big extinction event 65 million years ago. So, whoops, hold on a second. So an overview of what we're going to be talking about. In the very early Earth, we think that the solar system was a pretty dramatic place. There was all kinds of rocks and stuff flying all over the place. And a lot of major impacts were slamming into the Earth. And that ended about 3.8 billion years ago. During that time, just before that time, the Earth was basically uninhabitable. There was just so much energy being transmitted into the Earth. It was like a molten, the seas were basically molten lava. There could be no liquid water. But after this period of early heavy bombardment, things kind of settled down, and that's when life started to arise on Earth. Interestingly, though, we think that some of these original impacts may have delivered very important molecules to Earth that eventually allowed life itself to exist. So for example, water, we think a lot of the water that exists on Earth, in fact, maybe most of the water in the oceans, were delivered to the early Earth by these impacts. Today we know there's a bunch of near-Earth asteroids, so kind of big things that are up to sort of a kilometer in size that aren't that far away from the Earth, and some of them have orbits that bring them close to the Earth, and so these are things that we're constantly tracking. We wouldn't want another one of these big events like the event that killed the dinosaurs to hit us, and we'll talk a bit about that and how we track those things. I'll talk a bit about the evidence we have for this big impact 65 million years ago, why we think it played a fundamental role in destroying the dinosaurs, and then I'll also talk about other big extinction events that we know that have happened, for example, in the last 500 million years or so, and possible causes of those extinction events. So let me remind you again, I've shown you something like this before, but there are basically 4 eons or major divisions of geological time that we talk about. There was this Hadean eon, and this was the eon before life. We think that life arose after this point basically because these big bombardments stopped after that. Then there's this period of time called the Archean. That's when we think the first life arose, possibly at the bottom of oceans near hot volcanic vents. The Proterozoic happened only about 500 million years ago, and this was actually the first multi-celled life. So as soon as life became sort of complex, that was only 500 or so million years ago. And finally, the Phanerozoic, sorry, I got that date slightly wrong. The first multi-celled life arose about 2.5 billion years ago, but the first animal life, the sort of complex animal life, arose only about 500 million years ago, and that marks the Phanerozoic. Now, I mentioned this briefly before, but there was this period of time in the early solar system where the solar system was a pretty violent place. really we think that the formation of the solar system started to occur maybe 4.5 to 5 billion years ago. During that time, the sun had just formed, and there was a disk of material on the outside of the sun that was sort of orbiting around.
So I'm making an announcement for a special event. We're going to come right before you dismiss to make a quick announcement.
Sure. Yeah.
You guys are done at 11:50?
No, we are done around 12:10.
Okay, cool.
Okay.
See you then.
Yeah.
Thanks.
So there was this period of time where the very early solar system where there was stuff orbiting around the sun, and when small bits of stuff began to glom together, those were the cores of the planets. And the planets began to grow. As they built up gravity, they began to attract more stuff around them, and the planets began to settle out into this disk. But all this sort of shrapnel that was left over from the very early part of the solar system was still flying around even after the core of the Earth had formed. And some of this stuff would occasionally just slam into the Earth and deliver all kinds of energy, heat it up. And this was this period known as the late heavy bombardment. We think during this time there were water-rich comets and asteroids that were slamming into the Earth. And we think that possibly these water-rich objects were delivering water to the Earth itself, and this is what perhaps gave rise to the water that makes up our oceans. But also, there was carbon from these meteorites that was being slammed into the Earth, and we think that the early Earth's atmosphere had a fair amount of nitrogen, and that carbon and that nitrogen may have combined together to create hydrogen cyanide. Now, there's this idea that this cyanide was a pathway for taking carbon and putting it into the sort of chemistry of life. So, for example, chemicals that may have formed in interactions with this cyanide could have generated the precursors of, for example, lipids, nucleotides, and amino acids. And if you recall, lipids are the things, these sort of fatty things that make up the cell walls that sort of create bags for cell chemistry. This is important because you can have different kind of chemistry going on inside that cell compared to your outer environment, and that allows sort of the processes of life to maybe get going. The nucleotides that could have formed that way, these are the nucleotides that store information in cells. And then finally also amino acids, and these amino acids are the things that enable proteins to that can be assembled together to form proteins, and these proteins control metabolism, control this way in which life actually uses energy from its environment to sort of make things happen. So it could be that during this period of time where all of these bombardments were happening, some really essential things were happening to deliver important key elements for life. None of this is sort of set in stone. We don't know this. These are just sort of ideas that people have for the beginnings of the Earth. Yeah.
So if you believe that one of those or a couple of those asteroids did bring a large amount of water and certain precursor molecules that
Yes.
were necessary to in a sense create life on Earth, I guess that can happen with any planet, right? So
Yes.
what we are trying to do in this class is trying to figure out how can we go out and find life.
Yes.
It would be a better idea to first try to figure out what kind of asteroids carry this kind of molecules or could have been that and try to see their path and see how their path would interact with the path of some life.
Definitely, yes. So the question is, if these asteroids really were delivering these key constituents for life, including both water and these fundamental things that maybe led to life, why don't we look at the asteroids themselves to try to get a clue for where life might be? Why are we so worried about other solar systems and that kind of thing? Let's start with the asteroids. That is one thing that's actually happening. And so one of the drivers for people to go out and study asteroids and comets is to actually study the constituents of those asteroids and comets, figure out what kind of water they have on them, what kind of elements that they possess, whether they have organic molecules or not. These are exactly the questions that drive people to study these things. And I will touch on that in this lecture, but if you're interested in that kind of thing, there's a lot of literature out there that you can sort of find and begin to look at. But keep an eye on that, because we have a goal to actually send missions to asteroids. ESA has recently landed a probe on a comet, you may remember in the last year, and I'll talk about that. And so we're going to start learning more and more about comets and asteroids in our own solar system within the next few years, for sure. So yeah, that's a great question. So right, so that's one of the reasons, you know, it's just sort of this fundamental question, where did life come from on Earth? How did the early Earth get set up with the conditions that allowed it to have life evolve on it? These are the questions that drive people to go out and look at the asteroids and comets that are orbiting around. Because you could think of those as sort of like fossils or sort of leftover, sort of frozen in pieces of the very early solar system, these sort of initial conditions that eventually gave rise to what the Earth became. So this late heavy bombardment was doing all kinds of things, but one of the important things is you have things that are almost a sort of 300 kilometers across, 300 to 500 kilometer across things. I mean, that's big, really, really big things slamming into the Earth during this time, right? And this would have vaporized the oceans, it would have created magma seas, and this would have clearly wiped out at least any kind of life that we know about on Earth. And so that's why we think these were sort of sterilizing events, but these sterilizing events ended just a little bit less than 4 billion years ago. Now, this is sort of an age of surface deposits as measured on objects in the solar system that aren't like the Earth, that don't have the kind of geology that turns over the surface. For example, you can look at the surface of things like the moon and the surface of asteroids and things like that and try to get a sense of when the craters were happening, right? Because these bombardments were creating craters. You measure the rate at which this cratering occurs. And so what's happened is we think that it looks like the rate of cratering, so the rate of impacts, has been declining steadily for the past 4 billion years. And in the last billion years or so, it's kind of leveled out into a roughly constant rate. And so while early on, that's when most of these big impacts are happening, there are still a few that are happening, it's just the rate has dropped off. So there's this period of time in the early solar system where there's lots of rocks everywhere. Those rocks are slamming into planets. But eventually, most of that stuff gets cleared out over time, and what's left are just a few things now that occasionally their orbits might get perturbed, and then that sends them careening and hitting a planet every now and again. So this impact rate has really tapered off in the last billion years or so. So here's an image of a comet that we know about. This is actually the comet that the ESA probe landed on late last year. This is called Comet 67P. It's a few kilometers across, so it's a big thing. It's not as big as the things that were slamming into the proto-Earth, but this is how big this thing is. And this is the city of Los Angeles down here, if you can see it down at the bottom. Okay.
Is that the city or county?
Well, this is downtown LA, so
Okay.
you can sort of see it there. So it's a few kilometers across. I mean, it's not as big as the county of Los Angeles, which is much, much bigger than that, but it's, you know, it's huge. So this is kind of how big it is compared to, you know, the tallest skyscraper in downtown LA. So these things are big. If this thing hit the Earth, it would be bad. Okay, this would cause some bad stuff to happen if something like this hit the Earth. And comets, by the way, are moving really fast when they come close to the Earth because they're coming from very far away. And so these are the kinds of things that could cause big bad things to happen when they hit your planet. Now, a couple years ago, something about 1,000 times smaller than this actually came and hit the Earth. And I'm going to show you some movies of when that happened. I don't know if anyone remembers when this happened, but this happened a couple years ago outside the Ural Mountains outside of Moscow, about 1,500 kilometers from Moscow. Here's a dashboard camera from a car someone was driving in, and here's a big ball of light in the sky. And so this thing was streaking across the sky. So one of the crazy things that when this happened, do people remember this? Yeah, so if you remember when this happened, we learned a few things. First of all, apparently everyone outside of Moscow has dashboard cameras in their car, because like everybody has them. And you have these great movies. So like in this one, you really get a flair for what's going on, because you can hear this kind of weird techno music this person's listening to while this is happening, and like there's no pause, there's no breaks. It's just like rolling with it. So it's cool. So anyway, this great giant light in the sky. Remember, it's 1,000. This thing that hit is about 20 meters in diameter. Okay, so this thing is just this tiny little thing, much, much smaller, 1,000 times smaller than this thing when it hit, and it create this huge, great light in the sky. Here's the meteor event. It actually broke into pieces, so it came into the atmosphere, got heated up, and that's what created this great ball of light. And the thing broke up into pieces as it was coming through the air, and it created multiple streams like this. it basically blew up in the upper atmosphere and deposited most of its energy in the upper atmosphere. And that's kind of thing that happened. It blew out windows, knocked people down. You know, more than 1,000 people were injured in this event. So this movie is crazy because you really see this happened pretty far away from where the actual explosion happened, but it blew out all kinds of windows. So you can see, watch this guy, it knocks him down. And they don't know what's going on. Like, people thought it might have been a war or something. People had no idea what it was, and then they're sort of like ducking out in case it happens again. So it actually produced an incredible amount of energy. About 500,000 tons of TNT worth of explosion was deposited in the atmosphere. And that's 30 times more powerful than the atomic bombs that were dropped during World War II. Most of the energy was actually deposited up high in the atmosphere, and that's why more people weren't hurt by this explosion. Whereas, you know, bombs tend to put most of their energy down near the ground where the people are. And so a lot of people died that way. But the shock waves sent off car alarms and shattered windows all over the place. And really created, you know, this is sort of, you know, all these windows got blown out and stuff just from this sonic boom from this thing when it came in. So it just gives you a sense of, you know, the kind of power that these things have. Even something that's relatively small. We had no idea this thing was coming, by the way. We don't track things that are this small. It had a relatively soft landing. Here's the sort of crater that it left. This was a frozen lake, and it created sort of a 10-meter wide hole. And there were sort of the fragments of this thing that were left were only about 1 centimeter big after they had kind of burned up in the atmosphere. So these fragments that were like 1 centimeter in size, these tiny little things, created, there it is, there's one of them, created this giant crater when they hit because they were moving so fast. That's the kind of energy these things deposit. This was really fun. If you remember that, it's like the internet blew up because this was like the first meteor impact of the internet age, so there was all kinds of like fun stuff. I like this one a lot. I'm always a big fan of Chuck Norris too, so that was good. The funny thing about this is there was actually a meteor that we knew about that was coming near the Earth that day. And so when this thing happened, the first reaction from everybody was that, oh, maybe it was a piece of this other thing that was coming. Okay. So, so what was going on is that here is the Earth, and this Russian impact, this impact that happened on the same day, was actually coming from this direction from the Earth. Okay, here's the Sun, and here's the Earth. This is the orbit of the Moon going around. There was another asteroid that everybody knew about that sort of astronomers were looking for. That was called 2012 DA14. That was much, much bigger. That was like 50 meters across, so even bigger than this Russian meteorite. And so, you know, here's the size of the space shuttle. The thing was bigger than the space shuttle, and it was coming this way. We knew that one was big enough that it had been discovered already, and people had tracked it, and we knew it was going to come well within actually, it was going to come well within the orbit of GPS satellites, so it was actually getting pretty close to the Earth, but it did miss the Earth. So it was kind of weird that these two things happened in the same day. And when these things first happened, people initially thought, well, maybe there was some shrapnel from this that was coming off, but then people got a directionality from it, and they knew it was just something completely different. This thing here, the bigger one, was actually discovered in February 2012. That's why it was called 2012 DA14. At the time it was discovered, people didn't know whether they got an initial estimate for its orbit based on the measurement they had at the time, and it was consistent with hitting the Earth. And so people were then concerned that this big thing was going to hit the Earth, and that was going to cause, you know, as you can tell, it's much bigger than this thing that hit the Ural Mountains. So this would have caused probably some pretty serious damage, so people were nervous. But eventually they got the orbit exactly right, and they realized that it was going to miss the Earth by this much. So it came here, and there's the Earth. That's actually a very close call for something like this. So these kinds of things are out there. We hopefully are going to discover things that are this big within a year or so of when they're going to come by. So when you have a 50-meter asteroid, something like that big compared to this big, you can get pretty significant events. So this crater, this is the Barringer Crater in Arizona. It's about 1 kilometer in diameter, so it's a big, big hole. It's 170 meters deep. And this thing probably hit the Earth about 50,000 years ago. So things like this do happen. The bigger ones happen less frequently, so that's good. But we have evidence that things like this are hitting the Earth. You know, they do occasionally hit the Earth. Yeah?
If we know that an asteroid is going to hit us, can we really do anything?
Yeah, that's a great question. I'll return to that at the end. So the question was, if we know an asteroid's going to hit us, can we actually do anything about it? Not much. But if we had enough lead time, we could do something. And the question is what exactly we do. And I'll return to this in a bit. The thing you could do almost certainly is we would be able to calculate where it was going to hit. And so we would at least know whether or not to evacuate certain areas. So if it was small enough that it would be a localized bit of energy. So for example, if we knew the Ural Mountain thing was going to happen, probably what would have happened is you would have treated it like a tornado or something, and people would have just gone underground and gotten away from windows. Because you sort of would have had a sense of what was going to happen. Now, something much bigger than that was going to happen, you might even think about actually evacuating the area. So, you know. Yeah, did you have a question?
Is there anything left on the meteor?
I think that there was a meteor left here, and I think if you go to, there's a museum that's not far from here, and you can actually see it, I think. So things like this size, they will often be something left sometimes. So occasionally there'll be something left. It turns out a great place to find meteors is Antarctica. Because it's not because they only hit there, it's just because it's white there. You know, it's a white snow, and then they have these sort of dark things just kind of sitting out. And that's actually a place where people go hunting for these things. Otherwise, they're really hard. The little ones are just hard because they just scatter out, and it's hard to find them. A famous event that happened in 1908, also, you know, well, in Siberia here, not too far out here, is known as the Tunguska River event. And this thing was very mysterious at the time because people didn't really know what it was. And you'll still see this, you know, people talk about this mysterious event in sort of these like Bigfoot type of shows that they show on the sort of science channels, where they try to make this into some kind of UFO thing. We know, we have pretty good, well, we're pretty sure that this was some kind of meteor impact. We think it was an airburst, that it was like this Ural Mountain thing, except more powerful, and it blew up about 10 kilometers in the sky. And it estimated that it released something like 10 million tons of TNT. So this was more powerful than the Ural Mountains event. There were eyewitnesses, you know, that people reported from this time, that they felt a heat blast from this crazy event from about 50 miles away. So people felt this thing depositing all kinds of energy. It knocked forests over. So all these trees were sort of laid down by this event. There was seismic activity recorded 1,000 miles away. It was probably a comet because it deposited so much energy that it was probably moving very fast, and comets move faster than asteroids typically. It was probably a comet 40 meters in diameter, so a big thing. It was similar in size but faster than this DA-14 thing that I showed you. And these kind of things probably ought to hit the Earth on average about once per 100 years or so. Yeah?
What's the difference between a comet and an asteroid?
So I'll talk about that in a second. Comets tend to be icy. They tend to have more ice and less rock, and so they'll burn up a little bit faster. They also tend to live or come from the outer solar system where it's colder. So asteroids are rocky, and they tend to live closer to the sun, and comets tend to be coming from farther away. They have more ice, and they're sort of coming in these plunging orbits. But I'll talk about that in a bit. So in fact, here's a little bit on that. So here's some words in case you're sort of interested in knowing some words. And I sort of found this little diagram that I thought was very nice. A comet, okay. Comets tend to have these plunging orbits. They're coming from the outer solar system. They're sort of coming from far away, so that when they get in, they come fast. And they tend to be moving fast when they hit the Earth. They also tend to have a lot more ice on them because they're coming from farther away where it's colder. Asteroids mostly live in something called the Asteroid Belt. I'll show you where that is in a second. They live not too far from Jupiter, and they will occasionally, most of them sort of live in these nice, pretty stable orbits, but occasionally they'll get perturbed and come careening into the inner solar system and smack into the Earth. They tend to be rockier, so a little bit denser than the comets. The meteoroids are, I mean, I'm not going to test you over these names, but in case you hear them, Meteoroids are things that are too small to be seen at a distance, and so you only discover them when they hit something. So it's sort of a working definition. But anyway, if you hear the word meteoroid, that just means you don't see it until it actually hits something. You didn't see it before while it was orbiting out there. The meteor is actually a thing that lights up in the sky. Okay, so it's the ball of light you see in the sky. And a meteorite is the thing that doesn't burn up entirely, that you actually find lying on the ground. So if you're interested in these words, that's what they are. So, so one of the things we're interested in is how much energy, how powerful are these impacts going to be? And the way you basically can estimate that is we know how much energy they have based on their kinetic energy. So kinetic energy is one way that things can have energy, and it's basically the energy of motion. And it turns out that the kinetic energy of an object of mass m is equal to this. So if you have an object that's moving at a velocity v, its kinetic energy is 1/2 times its mass times its velocity squared. So that's how much energy something can deliver or impart, the amount of work that thing can do because of its motion. It goes like the velocity squared times its mass. That makes qualitative sense, right? If something's moving faster, it's going to deliver more of a punch when it hits. And also, if it has more mass, if it's moving the same speed, it's obviously going to hurt more if you get hit by a bowling ball than if you get hit by a baseball, moving at the same speed, right? So for example, the Earth is moving at about 30 kilometers per second around the sun. So that's a typical speed for rocks to be orbiting around the sun. Somewhere around 30, 10 to 100 kilometers a second, sort of the speeds. So anything orbiting the sun is going to have a velocity in this range. So we kind of know what this velocity is going to be, modulo sort of a factor of 10. But the masses can be, you know, hugely different, okay? So you can have a huge dynamic range from sort of, you know, less than 1,000 kilograms, that's things that are about a meter in size, up to things that are sort of 10 to the 17 kilograms, things that are 30 kilometers in size, some of the biggest things, right? So you can have things that are 10 to the 17 in mass compared to sort of, you know, 10 to the 3 in mass. And so that can create vastly different amount of energy when they slam into the Earth. So, for example, imagine you've got something that's moving at 10 kilometers per second, and it has a mass of about 10 million kilograms. So this is sort of similar to this Russian meteoroid thing, the Russian meteor that slammed into the Earth. I say meteoroid, but I used it wrong. I just meant meteor. So if you took the mass here, 10 to the 17 kilograms, and you plug in 10 kilometers per second and you work these numbers out, it turns out that a kilogram kilometer squared per second squared is something called a joule, the type of energy. And these numbers work out to something like 10 to the 15 joules. So 10 to the 15 joules, it turns out, is about the same as 240 kilotons of TMT, and that's about 10 times more powerful than the atomic bombs dropped during World War II. So again, these are the kind of things we're talking about that wouldn't be that rare hitting the Earth. See, fortunately, the Earth is very big, so the odds of one of these things is going to actually hit a populated area. You know, most of these things are probably going to hit over the ocean. But every now and then, you know, you get something hitting a city, and then you get these dashboard camera things. But you could also imagine you got something going a little bit faster, but not unreasonable, but 10 times bigger. So that's similar to this AD-14 asteroid that flew by in the same day. Had that thing slammed into the Earth, well, then the numbers go up a lot. You get a factor of 10 bigger in mass, a factor of 3 bigger in velocity, but then that comes in squared. So then this ends up being something like 10 to the 17 joules, or 24 megatons of TNT. That is a huge, huge explosion. Okay, that's similar to the most powerful atomic device ever tested. So this is something that the United States, at least that we know of, this is something the United States tested some time ago that created this crazy, sort of a crazy thing. But you know, it had a mushroom cloud that was 100 miles high and sort of incredibly powerful. This thing would give third-degree burns 60 miles away. Okay, so if something like this hit the Earth, it would be a pretty bad thing. There's this kind of fun thing. If you're interested in this kind of stuff, you can go to this www.purdue.edu/impactearth, where they have this whole thing where you can sort of dial up your scenario for exactly the kind of crazy stuff that would happen if a thing of a given mass and a given speed hit the Earth. And they talk about creating crazy tsunamis. So if this thing, you know, if you had one of these big things that hit in the ocean, it would create a giant wave, and these giant waves would wash over the land and be very destructive. So they look at all this kind of stuff if you're interested in this kind of scary whatever. If you're into that thing, I don't know who's actually into that, but if you're into that. Okay, so again, this is this size of asteroids versus energy. So this is this DA-14 thing that I said flew by on the same day that the Earl Mountain object hit the Earth. This thing would have an impact energy of the most powerful atomic devices that have ever been created by humans. This object here would create something that's 10 times more powerful than the bombs dropped during WW2. So this is sort of the range of sort of stuff that you know, that's out there, that sort of we're marginally seeing things like this, and we're not really catching things like this. Here is another thing. This is one of the bigger asteroids that's out there. This is called Gaspara, 951 Gaspara. This is an image that was actually taken by Galileo, so that's a real image. The Galileo spacecraft, not Galileo. This thing is 15 kilometers across. Okay, it's 50 meters, 15 kilometers. So to scale, that's the size of this thing that would create an impact that would be as powerful as the most powerful atomic device ever created. And this is this big asteroid. It's one of the bigger asteroids we know about, right? And by the way, this thing is small compared to the things that we think were slamming into the Earth during the Hadean era. Okay, so that's big. Fortunately, this object is tucked away safely inside the asteroid belt, and it's just orbiting there, and it's not on an unstable orbit, and it's probably going to stay there for a very, very long time, so we don't have to worry about it. What is the asteroid belt? Well, there's this region out inside the orbit of Jupiter, but outside the orbit of Mars, where there's a collection of asteroids that are just sort of orbiting around and sort of trapped in that kind of gravitational well, sort of going around this way. Okay? There's another bunch of asteroids that are trailing behind Jupiter's orbit, and there's another bunch that are trailing in front of Jupiter. Jupiter is this big, massive thing, so it sort of controls a lot of dynamics of the solar system. So there's other asteroids that are out there. Okay? So they're sort of orbiting around. There's about 1 million asteroids in the asteroid belt that are bigger than a kilometer across. Okay? There's a bunch of pretty big things out there, but there's only 100 that are more than about 140 kilometers across, these gigantic ones. So the super duper gigantic ones that are basically would be, you know, catastrophic for life on Earth, there's not that many of them, and the odds of them hitting the Earth are very, very small in the near term. By the way, something that's not so obvious here, the asteroids are really far apart. Okay, so you get the sense of sometimes you watch space movies or, you know, Star Wars or something like that, that the asteroid, you know, an asteroid belt is sort of like rock and then another rock and they're very close to each other. It's not really true. You know, if asteroids were the size of a potato, the nearest asteroid would be in another city. So they're very far away from each other compared to the size of the things. Space is very big. These asteroids are rocky things. They also tend to have a lot of metals. So one of the things people are potentially interested in doing is going to asteroids and mining them for precious metals. I don't know if there's real economic feasibility in that, but there's definitely people looking at that as something they want to do. They're pretty dense things, so they're denser than water, and they can be pretty big. So anyway, here's a few. This is that one that I was showing you before that looked so big. Well, here's a couple more. So there are things that are just pretty darn big out there. Comets, on the other hand, come from farther out, and they tend to come from something called the Kuiper Belt. The Kuiper Belt is sort of a group of icy bodies that are orbiting outside the orbit of Neptune. And they tend to be the place where most comets live because it's cold. They're sort of these icy things. And every now and then they have these plunging orbits that bring them in close to the sun. There's another thing that's even farther away from the Kuiper Belt that's called the Oort cloud, where the really, really long period comets come from. They're coming from really, really far away, and they're moving very fast when they come in to the Earth. We have never actually, we think the Oort cloud is there because we see comets coming in with orbits like this, and you can sort of estimate, you know, they're going to turn around somewhere out there. But we've never actually been able to detect anything that's way out in the Oort cloud because the Oort cloud's really far away. And some people estimate that it might actually spread out light years out from the Earth, from the sun, and perhaps the Oort clouds from two stars might even kind of touch each other. You know, it's that they go that far out. Something just so you sort of have seen this before. You probably have seen that comets have tails, right? So comets have these kind of pretty tails that come off of them. Maybe you've seen pictures of them. What is that? So the thing to keep in mind is that comets spend a lot of time way out here, way away from the sun. And the ice, they can have this sort of cool ice surfaces. But when they start to approach the sun, things start getting warmer. And a little atmosphere begins to form on the outside of the comets from just sort of evaporating stuff. And when they get very close to the sun, the solar wind and energy from the sun begins to kind of push this tail of the comet off. And there'll be a dust tail and then also sort of a tail of sort of stuff evaporating off the, from ions that are being pushed, sort of ions that are being pushed by the solar wind. And so that's why you tend to have these tails push, you know, it looks like the comet has a head and then this sort of tail coming behind it. It seems like, you know, if you've got a head and a tail, that it ought to be moving this way and the tail is always right behind the direction of its motion. That's actually not what the tail is. The tail is always pointed away from the sun. So, you know, even though if you have a comet that's moving this way, it'll have a tail pointed that way, always pointed away from the sun. But anyway, that's what the tail of the comet is. And again, they have these tails because they're made up of this icy stuff that evaporates very easily when they get close to the sun. Then when they come back away, that stuff cools down again and they don't have that so much anymore. In November of 2014, we did this kind of amazing thing. So we, the royal we, ESA actually landed a robot on the surface of a comet. So there was a mission that was called Rosetta, and Rosetta had a little lander on it that it launched off of it that landed on this comet, which we could call P67. Getting there was kind of crazy. So here's the orbit of the comet that it landed on, right? Here's the sun, there's Venus, there's Earth, there's Mars, and you see it's sort of, and there's Jupiter. So this is sort of a nearby comet in the scheme of things, and it orbits like this. And what this thing did is, it actually did a bunch of loop-de-loops around the inner planets to get there, to kind of speed itself up and to get it positioned to be moving along with the comet when it did. And finally, it sort of rendezvoused with the comet. You know, the comet's orbit was here, and it sort of came along and rendezvoused with the comet and then sent its lander to land on this thing. This is a picture of it that was taken by the spacecraft just before it sent the lander on it. So it's like a really amazingly detailed picture. Notice that it's not round. It's kind of clumpy looking. And that's because things don't get round until they're so massive that the gravity overcomes the strength of the rock to push it into sort of a tight sphere. So gravity is constantly wants to make everything equal. Okay? So if this thing had enough gravity, its self-gravity would just smash it into a sphere. But it doesn't have that much gravity. It's not quite that big enough, and that's why it has this kind of funny shape. And so comets and asteroids, especially if they're smaller, tend to have shapes that are not perfectly round because their gravity is not strong enough to make them spherical like planets are. So planets tend to be spherical, well, they are spherical because they have so much gravity that makes them spheres. This thing is quite big, and so they publish all of these pictures. Here's the Eiffel Tower in comparison. Okay, here's some famous mountains in comparison. And so there's all these things. You know, this thing is quite large, and so we landed a little object on there. It's pretty cool. So these objects, these icy bodies that live in the outer solar system are generally called Transeptunian objects. They tend to be made of mostly ices, and therefore they're less dense. Yeah?
How much gravity was on that rock?
How much gravity? Not that much.
I mean, did they have to use like hooks to just...
Yeah, they did. So it was actually what the thing did. So it turns out that they had a little trouble landing it. There were a few issues. But it came in, and they thought, what was the issue? They thought it was going to be softer than it was, because there's some evidence that there are comets that are extremely soft, like shaving cream soft stuff. And they had this idea that it was going to come in, it was going to hit, it was just going to grapple on and not bounce back up that far. but because there's not that much gravity, they really had to rely on sort of losing some energy, like sort of plunge into the surface a bit when it landed. But it wasn't. It was harder than they were thinking it was going to be. So it came in for sort of a hard landing. And then it bounced way back up. Like I can't remember how far, but it was like a couple, maybe even a couple kilometers back. So it hit and then it bounced. And the gravity of the thing was so weak, it took a really long time to bring it back. And so one of the issues it had was that that landing was hard because of the fact that it doesn't have that much gravity. And so landing, it was a great question, because landing on these things, that's one of the things that makes landing on these objects hard, because it just doesn't have that much gravity. You know, unlike the moon, which has a fair amount of gravity, you know, you land on it and you're going to stay there. This thing really doesn't have that much gravity. So it makes the whole process pretty tricky. Yeah, it's a good question. Any other questions? Yeah, so anyway, I'll just sort of throw this up there. One of the sort of frontiers of solar system science right now is trying to track all the things that are out there beyond Neptune. And this is one of the, you know, is sort of looking for these objects beyond Neptune that eventually led to this idea that Pluto's not a planet anymore. So at this point, we've discovered a bunch of things that live beyond Neptune that have kind of cockeyed orbits like Pluto does. And that's why we now sort of have this new classification of sort of smallish things that don't have that much gravity to clear out their orbits, that are now just called dwarf planets. And Pluto was the first of the dwarf planets to be discovered. There's also Eris and Makemake and Waimea and a bunch of other little things. And a lot of these things have their own moons. This is sort of just to give you a sense then. The asteroids, so this is a sort of mass of the objects that we know in the solar system. These are the distance from the sun, the typical orbital distances from the sun. The red things here are all the planets. You see they're very massive, so masses along this axis. You've got moons. The big moons here are shown in orange, and the dwarf planets here are shown in purple. Here are asteroids. They tend to live in the asteroid belt, pretty low mass things. And then in the Kuiper belt, way out there, there are these other things. And like I said before, most comets come from the Kuiper belt, and then most of the asteroids are living here. So these are the things that might slam into the Earth or could have slammed into other planets along the way. The near-Earth objects we're worried about, okay? These are objects that have orbits that bring them near the Earth, and they're pretty big. Here is the total number of objects that have been discovered, okay, that we know about. There are 6,400 of these near-Earth asteroids that are known, but we know that we're incomplete. We know that we don't know where all these things are, because they're pretty hard to find. And so we think there's probably 20 times more of these things that we just don't know about. And there are probably 1,500 or so of these things that are more than a kilometer across. So in principle, there's stuff out there that could hit the Earth. And there's sort of a campaign now to begin to figure out where these things are and figure out what you would do to stop them. I'm going to skip this. Okay. Now, so let's go back to talk about the history of the Earth. So there are craters like this that are found on all continents. So we see evidence that these craters have happened, and they haven't all been washed away. For example, this is a 55-meter deep crater that exists in Wolf Creek Crater, Australia. This happened about 300,000 years ago. Okay, so it's not, again, not that long ago. It's older than the one in Arizona that we showed before. This is another crater that was actually discovered by satellite imaging. It's in Quebec. We think this came from a 5-kilometer size asteroid that hit about 200 million years ago, and it actually created this sort of crazy pattern. That's why this sort of water formation exists. So the very ancient impacts, let me remind you, that were happening, that were sort of 300-kilometer size things. These are the things that were just wrecking the planet. That sort of ended out about 4 billion years ago. Even before that time, about 4.5 billion years ago, an even bigger thing that we think was about the size of Mars slammed into the Earth. And when this happened, a piece of the Earth broke off and became the moon. So the moon actually formed about 4.5 billion years ago, sort of coevally with what we think of as sort of the Earth now, broke off a piece of the Earth and began orbiting around the Earth, and that's the moon. We have this crazy big moon. Okay, our moon is, I think, of the biggest, maybe the second biggest, third biggest moon in the solar system, okay? Even though our planet isn't that big. So we have a crazy, crazy big moon compared to the size of our planet, and it had this kind of weird formation. It basically formed from this event where it was effectively a piece of our own planet broke off and became that moon, became our moon. So more recently, even though the number of these impacts has fallen down, we see evidence that they continue to go on. And in fact, we think that some of this stuff might be related to mass extinction events that we've seen in the history of the Earth. So what's shown here is basically the number of species that exist on Earth plotted as a function of look-back time. So this is about 500 million years ago. Remember, animals first evolved sort of around this time. So we're sort of looking at animal species here. So we see that over time the number of animal species is increasing, and then occasionally there are these sharp drops in the number of species that exist, and these are just known as extinction events. So there were, for whatever reason, there were sort of large extinction events that happened now and again. And the most recent one happened in the late Cretaceous about 65 million years ago, right here. Okay. This was the last major extinction event on Earth. And this is the event associated with the extinction of dinosaurs, again, 65 million years ago. Interestingly, if you go and you look at sediment deposits, if you dig down into the Earth until you get to sediment deposits that correspond to this period of time when this mass extinction happened, you see something that's pretty interesting. Okay? You see that there's a layer of material that's unusually rich in iridium and soot. So specifically, 100 times as much iridium exists in this layer than exists elsewhere or naturally on Earth. So there's all this sort of extra iridium there and soot there that just seems kind of out of place. Okay? Interestingly, that level of iridium is comparable to what you see in asteroids. So it's this piece of evidence that gave people the idea that maybe the thing that marked the transition between below this point you have dinosaurs and up here you don't, was that there was a major impact event from an asteroid that kicked a bunch of stuff up in the atmosphere that had then settled down into this layer that marked this transition. Okay. Again, at this point, 75% of land and marine species, including all non-avian dinosaurs, went extinct at this point. Okay. And mammals became, this is sort of flipped the axis. This is long ago and this is today. Okay. It was only after this point that mammals began to dominate the Earth. So before that time, it was sort of, the animals were sort of, dinosaurs sort of dominated the niches, and then after that, mammals began to take over. So the mammals did not go extinct during this event, primarily because they were probably these little small things that, and that could live in bushes and stuff, or live underground perhaps. And they're also warm-blooded, and maybe they were more adaptable to sort of a sudden sort of decrease in temperature, etc. Now, the favored theory then is that there was this big asteroid that hit. And the idea is that this asteroid was maybe about 10 kilometers across. So again, pretty big, even bigger than that map that I showed against LA in the beginning. So it would have been something about 10 times that size. Okay, so 10 times the size that the Philaea, of this thing that the Philaea lander landed on, this Comet 67P, something like that. So this would have been 2 million times the energy of the most powerful nuclear bombs that have ever been exploded. It would have caused global firestorms and mega tsunamis all over the planet. It would have thrown dust up in the air, which would have blocked out 10 to 20% of the sunlight that would have been coming in, and therefore caused crazy, like, deep winters. So this would have been a very extreme event for the Earth to deal with. Interestingly, there is a crater that has been discovered that's about 200 kilometers in size off the Yucatan right here. Okay, it's a very interesting place. You see impact glasses there, which again is sort of the kind of thing you get when you have very, very high heat from deposits. We see a gravitational anomaly. So this is actually a gravitational map, and you see a gravitational anomaly of a crater there underneath the water. And if you do radiometric dating of the age of the crust right around there, it's spot on to 65 million years. So the story of this playing a fundamental role in the extinction of the dinosaurs seems to be pretty solid. There's sort of different pieces of evidence that point to this point as being important. Now it also could have been that when this impact happened, it actually triggered some volcanism. So volcanic activity may have sort of shot up at about the same time too. And then all of these things may have contributed to this mass extinction that happened at the time. Okay. So one of the things that we can then think about is, well, how often should these kinds of things happen? And so it turns out because there are way more big things, big rocks out there than little rocks, we think that the big rocks ought to hit the Earth much more infrequently than the little ones. The little ones will hit us all the time. In fact, little things are hitting the atmosphere all the time. Big things hit very rarely. And in fact, what's shown here is the object diameter as a function of roughly the mean interval between impacts in years. So for example, every 10 years we expect to get hit by something that has a diameter of about 10 meters or so. Okay? And every 100 years, for example, you might get something that's, or 50 years or so, you might get something that's like the Ural Mountain event. So this object that we talked about that had all the dashboard cameras. Okay, so that might happen every 50 years or so. This Tunguska asteroid, that might be, anywhere between 100 years and 1,000 years. We don't show exactly how big it is, but sort of something like this. This thing that killed the dinosaurs, okay, maybe every sort of 25 million years ago, 50 million years ago, and that's how long it's been. Okay, this thing hit us about 65 million years ago, and that is about every 50 million years, 100 million years is when you expect to get hit by something like this. Okay. Now, what's shown with the colors is the kind of destruction that you will get when these things hit. The bigger they are, the more energy they deliver, and the more destructive they are, right? So if it's in green, you think of it as sort of a local destruction event. So yeah, whoever is near, who's ever underneath the blast is going to have their windows blown out, and maybe you'll get some damage there. But if you're in green, it's going to be pretty local. You'll have regional destruction. That is, you might, the whole regional area, the whole county, or you might even think of possibly state will get some destruction if you're sort of up bigger than 100 meters or so. And so that's a little bit bigger than this Tunguska event. But again, if you're up into the orange, you're talking about a mass extinction there. There you're talking something that's going to have global effect on the planet itself and probably drive things to extinction. People characterize these things with different names. So people call, for example, there's things that are called city busters, people busters, and planet busters. So city busters are things that are 30 meters across. Okay? These kind of things should happen every 50 years or so. Again, it's sort of like Tunguska or the Ural Mountains event. You're talking about a megaton of TNT. And this will end up, if it happens right on top of a city, mess up that city. But it's not going to cause sort of mass death beyond that local point. If instead you had something that was a kilometer across, then you're talking about something that the atmosphere doesn't stop, okay? Something that's that big does not get burned up in the atmosphere. It just comes right on through the atmosphere. So then it's leveling all of its energy right onto the Earth, okay? It would create hemispheric scale or global effects. It would kill a lot of people. It would kill a lot of animals. So this would be a pretty big bad thing if this happened. We think these things ought to happen every sort of 100,000 years or so. A planet buster kind of event, the things that would create global extinction events, okay, are things that are 10 kilometers across. These things happen every 100 million years or so. Again, that's this sort of dinosaur event. This will, vaporize atmospheres, create mega tsunamis, really be catastrophic for life on Earth. Probably, it's hard to imagine that humanity could live through something like this. Any questions about this? Okay. So, it's interesting to think about this just sort of randomly. I mean, something like this is going to hit the Earth again. Okay. It will eventually happen. The question is, on average, it happens every 100 million years. So, we just don't know when, but It should happen again. The US Congress, for example, has given the US Air Force and NASA a goal to track everything within 150 meters that will get close to the Earth. So we want to know about everything that's potentially going to cause damage to the Earth. And we basically know, we think we know of everything bigger than a kilometer or so. Okay? So things bigger than a kilometer or so are these people busters. So we think we know about everything bigger than that. We don't know for sure, but we know for sure that we are drastically incomplete. What's shown here is in red the things we know about, and blue is sort of a guess of roughly what's out there. Okay? And so the Ural Mountain event was sort of one of these that we didn't know about. The Tunguska event was one of these that we didn't know about. Actually, it should be, yeah, Tunguska event was one of these we didn't know about. And so we don't really know about most of these things. We'd like to think that we're complete to the big ones, because the big ones are the really bad ones, and then these. So if we discover something that's coming near the Earth, at least we know about it ahead of time. So then it gets back to your question, which was, okay, fine, we know it's heading our way, but what the heck do we do about it? Okay, now that is actually a pretty hard question to answer. In principle, we have the technology right now to send something out there. But you would have to have time to build it. Okay, and it takes a long time to build these things. Okay, so you know, a typical space mission of a large telescope takes 10 years to build. Okay, so you hope that you give yourself at least a few years. We know something destructive is headed our way. You know, hopefully you have time to do something about it, but what would you do? You're probably not going to send Bruce Willis up there to blow it up. That would not be, that's not what you want to do. Because what would happen then is, rather than having like one big bowling ball headed your way, okay, you would blow it up, and now you would have like 1,000 little, you know, shrapnels of bowling balls headed your way. And so now it's just going to be a firestorm coming at you. So blowing it up is not going to help anything. So what would you do? Well, there's a few different ideas, and people aren't sure exactly what to do. But one thing, I mean, if you've ever, the easiest thing to do is you find out about it early, and you just give it a nudge. Okay? Imagine, right, you're shooting a three-pointer, right? The reason why shooting a three-pointer is harder than shooting a layup is because you have the ball has so much farther to go. And so if you're off an angle by just a little bit, right, you're going to be off by a lot when it gets there. It's the same thing with hitting a pool shot from across. You know, if you're trying to hit a pool shot from across the table as opposed to really close, it's harder from across the table because you have to get that alignment exact. Because the farther the ball goes, the more it's going to be off, right? So if you just alter the trajectory of that ball a little bit, right? If someone fouls you making a layup, you're probably going to make the layup. If someone fouls you while you're shooting a three-pointer, you're probably going to miss. It's just a little, you know, just touch your elbow and you're going to miss, right? So if we find something that's far away, you know, far away from the Earth, that's headed straight to the Earth, all you got to do is give it a little tug, a little tip, and it'll miss. So that's the idea. You don't want to blow it up, okay, because now something's going to hit, right? Even if you give something a tap, something's going to hit. Yeah?
If it's so far away, like how do we get to it?
Well, okay, so it's not like, great question. So if it's so far away, how the heck do we get to it? That's a great question, because right now we couldn't get to it. We could send, but we could send so the idea is we probably can't send people to it. Because right now we actually have no way of sending anybody farther than where the space station is. And the space station is really, really close to the Earth. There's plans in the work to build things that will be able to go, say, to the moon or nearby asteroids. So China is working on such a mission, and the US is working on such a mission. But right now, if we needed to send people out there, we couldn't do it. But we can send robots there, okay? Just like this Phyla lander landed on a comet, you could send something sort of robotic to go. And then what would you do? So there's different things. People have thought about the idea of actually sending something near an asteroid, and then you just put something near it that has some gravity to tug it gravitationally a little bit to get its orbit off, and then it would miss, right? Or you could set off a little explosion that was far away from it to sort of give it a push. Again, that might be dangerous because you might break something off of it, and you don't want that to happen. Or you could imagine just giving it a little thrust, attaching thrusters to it. Another idea that people have had is you could actually build a powerful laser. And you shoot the laser at it not to sort of blow it up, but you actually give it a push with the laser. with effectively with radiation pressure. So when light hits something, it actually is hitting and bouncing off and giving it a push. So you can imagine, sending a targeted laser to push on the thing and push it. Man, you don't have to give it much of a push if it's really far away. You just have to miss a little bit and it'll miss the Earth. Okay? So that's probably what we would do. Right now, we couldn't even do that because we just don't have, the question is turnaround time. If we knew for sure that an Earth-destroying thing was going to hit us in 2 years, we'd probably get something off the ground, right? I mean, all nations of the world would unite and put something together and probably make it happen. But that early warning is crucial. So if we only had a month, it would be bad. Okay, but there are other, so this is sort of, along the lines of like future extinction events, right? We don't want future extinction events. That doesn't seem to be too good. What about these other extinction events? Well, we don't know for sure that all of these events had something to do with big impacts. In fact, we think not all of them had something to do with impact things. A particularly interesting one is this one right here that happened in the late Permian about 250 million years ago. This is called the Great Dying. It was this sort of very catastrophic event where 98% of all marine species and 77% of land species all went extinct at the same time. There's lots of ideas for what caused this event. This is another way of saying it. This is the extinction rate, so the rate with which things are going extinct. You see there's this great spike here, right here. That's what we're talking about. People don't know. So, one idea is you go back to your asteroid, your comet, maybe something big hit, created. There is another thing, kind of an interesting idea that's become popular recently, is that imagine you've got all of these methane producing microbes. So you've got microbes at the seafloor that are producing methane. That methane would be poisonous to, for example, lots of animals if that methane were released into their environments, but they're sort of localized and perhaps under the crust. One idea is that you had some kind of massive thing, a big meteorite that hit, but it actually hit that part of the ocean, for example, and threw this stuff up in the atmosphere and created sort of a massive methane outburst into the atmosphere that would cause this mass extinction. And there's some evidence that sort of methane may have played a role in this great dying event. But this idea, the question of what created this great dying is one of the puzzles that people try to figure out. Whereas this thing that caused the dinosaurs, there's details that people are trying to work out, but we think it did have something to do with this impact 65 million years ago. The thing I want to leave you with, by the way, is that if you go back over Earth's history, you see these periods of extinction. And you think of that in terms of the history of life as kind of bad for life, right? Because life is dying. You're sort of killing these species. But what's interesting is those open up these ecological niches for other species to come along and take over. Okay, so you have now room for large animal. Before you had these big dinosaurs that kind of dominated the niche of sort of big things. When all those things get wiped out, there's now room for new species to evolve and to fill those gaps, okay? So then you have things like the giant mammals that began to evolve that we sort of have evidence for existing sort of 10s to 20,000 years ago, that eventually those also went extinct, but we know that there were these big mammals that existed those times. And today, of course, we have a few surviving large mammals like elephants and that kind of thing. So, it could be that when we have these things, although they seem destructive for life, they're actually sort of you can think of them also as sort of a boost to evolution that allow more interesting things to evolve. For example, it is not entirely obvious, and in fact it may not at all be the case, that had this rock not hit the Earth, okay, today there would probably be descendants of those dinosaurs, if not the same species, probably very similar species would be existing. It's not entirely obvious that those dinosaurs would have developed big brains and be standing here right now talking about themselves, right? It's unlikely, in fact. You could argue, is it inevitable that you were going to have this? Well, the dinosaurs had, the first dinosaurs basically came into being right around this time, about 250 million years ago. It was only 150, something like this. Well, they had, more than 100 million years-ish, to evolve those big brains, and it didn't happen. Okay? But in the last 65 million years, some things did evolve the big brains. So it's not entirely obvious that that big brainness is a niche. Okay? So while there are ecological niches, like for example, big animals, you know, you could think of other things as sort of niches that animals could fill. There are other things that are sort of more accidents of evolution, like for example, peacock tails, right? Peacock tails, it's not like, boy, there had to be a bird with the giant crazy tail that doesn't actually do them any good other than help them, you know, like attract mates, right? That's pretty much all the peacock tail is. So it's not like there's a niche for that, it's just sort of weird. Big brains could be like peacock tails, right? It doesn't have to be this way. Now that we've got them, we use them for what we've got them for, but it's not obvious that evolving a big brain is the best thing to do if you just want your species to survive, right? Because our brains take a lot of energy, right? So we have to eat a lot because we have these brains. So much more of our caloric energy, we have to eat so much more because of our, if our brains were small, we'd have to eat like half as much, right? So then you could think of it as sort of not a positive thing that we have these big brains. So, you know, it's sort of interesting to think about that. You know, you could argue like all of this stuff had to happen, all of this had to fall into place, and whatever reason, this rock hit the Earth, and then after that, that opened up a pathway for eventually these mammals to develop that ended up being sort of self-reflective and be able to make plots like this. So we'll talk a bit more about that kind of stuff as we move on. All right, thank you.